Biosensors are sensing technologies, molecular sensing technologies that employ a biological element to recognize the target molecule. That biological element could be a protein, it could be a DNA molecule, or even in some cases, people have employed whole live cells as the recognition element. But the key element, the key part of the definition of a biosensor is that biology is used to conduct the recognition. The amazing recognition properties of biomolecules has been acknowledged for about 75 years. And that in turn motivated at least 60 years of efforts to adopt biomolecules into molecular measurement technologies. 60 years of effort, and really to date, before our work, the only real success for in vivo measurements was the continuous glucose monitor that diabetics use. So 60 years of effort, one success. What's the problem? Well, the problem is most biomolecules don't do anything when they bind their targets. They just bind and sit there. They don't emit electrons, they don't emit light, they don't change shape, they don't do anything. By providing real-time information on blood sugar levels, the continuous glucose monitors that people with diabetes are increasingly wearing has revolutionized how we treat that disease. When you think about it for a moment, though, blood sugar is probably not the only molecule that clinicians and their patients might want to have real-time information on. The problem is, though, that the glucose monitor relies critically on the specific chemical reactivity of glucose. That makes the technology impossible to translate into the measurement of other molecules. If, however, you look at those receptors that biology uses to monitor specific molecules in the body, there's a commonality amongst all of them. In every case, evolution's engineered those so that when they bind their target, they undergo some big shape change. I'm a biologist. I took inspiration from that idea, and me and my research team set out to learn how to redesign the receptors that we could use in artificial technologies so that they would all also undergo a binding-induced shape change. And we then developed electrochemical methods of converting that shape change into an easily measurable output, and voila, we've got our technology. Now, I made that sound simple. In reality, it was about a dozen years between when we first had that inspiration and we finally got one of these sensors to work in vivo in a laboratory animal. And I remember that day very well. One of my postdocs, Netzeroya, who was really key in making that final breakthrough, came into my office and handed me the data. And he knew exactly what I wanted. He just, hug time, right, boss? I don't usually hug my postdocs, but I definitely did that day.